So today we will try to solve a PTB problem for elastic plastic stress analysis. So as per ASME Section 8 Division 2 Part 5, protection against plastic collapse can be validated by three different approaches. First one is elastic analysis, wherein we apply the load with the linear material. We run the analysis. We classify the stresses based on their location and their nature, like local or general, and primary, membrane, or bending. So, we evaluate the stresses, compare them with the allowable stress, and then we say whether the component is safe or not. Another method is the limit load method, which we'll talk about it in next session. The current area of interest, or the what we are going to discuss today, is the elastic plastic analysis. So ASME Section 8 Division 2 Part 5 give the clear guidelines how to perform the elastic plastic stress analysis, and they have solved that problem in solve problem manual PTB 3, and PTB 3 they are solving using the Abacus as simulation tool, and here we will try to solve the same problem using the NASTRAN, which is available at our end. So what we will learn today, or let's decide the agenda for today's call. So can we use Autodesk Nastran as a software to perform the analysis to meet the ASME Section 8 Division 2 Part 5 requirement? We'll see that. Uh, Another interesting topic we will be discussing today: can ASME Section 8 Division 1 vessel we design it using the rules of Division 2, and more precisely using the finite element analysis method? Uh, Another topic I will be covering is what is the good mesh to continue the analysis, and how to know that what is mesh convergence. Fourth topic we will be discussing about is the how to define nonlinear material in Nastran, because we are doing the elastic plastic stress analysis method. And fifth point is how to set up a nonlinear elastic plastic analysis in Nastran. And last point, which is important, is verification of result, comparing it with the PTB3 output, and matching the reaction forces in the Nastran. So it's going to be very interesting session today. So this is the extract from PTB3, wherein the problem number 5.2.3, elastic plastic analysis. So we are going to solve the same problem we solved for the elastic analysis method with the approach of elastic plastic analysis, which is explained in the Section 8 Division 2 Part 5. So vessel is same, material is same, only thing we will be changing it to the non-linear material. The internal pressure is same, but we will know or will understand more about how to apply the loads when we are doing the elastic plastic analysis. And this is the typical vessel configuration. We have seen it in first session also. Uh, Vertical vessel supported on the skirt, and the dimensions are provided here to construct the 3D model geometry. Uh, Here the mesh model is shown, and the axis symmetric model is made using the abacus. But since we are using Nastran, we will slightly modify this model in order to suit the similar boundary condition as well as the mesh size. So first of all, we'll understand the boundary conditions. Here you can see the at the bottom, the movement in y direction is restricted, as well as the rotational motion in z direction is restricted. So we can see the coordinate system xyz at this corner. Let's talk a little bit about our second question. Can we design a vessel uh, as per division 1 using division 2 rules? So when we go into the structure of division 1, there is a specific uh, appendix for it. So it's appendix 46, which gives the guideline how we can use the division 2 rules to design a vessel as per division 1. And uh, the the guidelines of how to use that appendix is given in U2G. So you need to refer to the clause U2G, and then again refer to the appendix 46 to get the idea or the get information. Can we use division 2 rules to design a vessel as per division 1? Now we'll uh, think or discuss a little bit about how to apply the loads. So table 5.5, which provide the load case combination and load factors for elastic analysis. So here the first design condition for the global criteria, beta multiplied by P plus PS plus D. So you can refer to the part 5. So beta is the multiplication factor, P is the internal pressure plus static head plus dead load. So this is the combination. Since in our case only internal pressure is the only load, we will be considering the first load case combination for design condition. And when we see the appendix 46, uh, where it is mentioned, when applying the elastic plastic stress analysis method in division 2 of 5.2.4 in conjunction with division 2 table 5.5, which is mentioned above, beta factor shall be 3.5. So that's the only, so we get answer what will be the beta for our case. There are different beta factor also, which is defined by the class of vessel. So vessel can be class 1 or class 2. Details of same are given in part 4 of the section 8 division 2. So if there again we have the another beta factor as 2.4. So you can go into that and see the detail. For the simplicity, we have taken the loads and the factor loads as given in PTB 3 problem. So our internal pressure now changed to the 1008 psig, and factor thrust pressure will change to 2357 psig. So we'll go into the NASTRAN window and we'll see how up to this point how the model is to be set up. So first of all, this is the quarter model I have prepared. Okay, and we can see, yes, this is the quarter model, and will accordingly modify the boundary conditions. So let's first understand the boundary condition. So this face which is perpendicular to the z axis, so I have applied symmetry along the z. So on this place, the face at the bottom is perpendicular to y-axis. So I have applied symmetry along the y, and the last face is perpendicular to x-axis. So I have applied symmetry along the x. So we have simulated the boundary conditions. Now next is the loading. So I have applied the internal pressure normal to the internal surfaces, and value is 1008 psig. And another loading we have is the thrust pressure, which is applied on the raise face area of the flange and its value. The negative sign is just to adjust the direction of the applied load. So, okay, and we have uh, mesh the model. So when we can switch on the mesh display, we can see the model is meshed using the point 3 mesh size. Okay, so let's talk a little bit about what is the good quality of mesh. So, how, or rather, I would say, how I arrive at this mesh size, and I say this is the correct or appropriate mesh size. So, this is the iterative process. At the beginning, you need to assume a certain size of mesh and apply that mesh size. Okay, and once uh, you can put that size over here, you run the analysis, you note down the what is maximum displacement and maximum stress, then again you reduce that mesh by some value and do again the analysis. So initially I run it with the zero point 0.7, then I run it with the zero point 0.5, and then I run it with the zero point 0.3. And in these two subsequent runs, when the by reducing the mesh size, my displacement is not changing or my stress value is not changing substantially. And as a practice, we assume if the uh, difference is not more than 5%, we can say we have achieved the mesh convergence. So mesh convergence is nothing but a size of mesh, wherein by further reducing the mesh, we are not getting any substantial change in the our stress output. So this point you need to keep in your mind. Now we have seen the constraint, we have applied the load, and we have also see the how to achieve the mesh convergence and run the uh, check whether the mesh size is enough or not. Next part is the how to set the nonlinear study. So in NASTRAN, when you have we are into NASTRAN environment, you click on the edit and you can see there are variety of analysis types available. I have selected the nonlinear static. Okay. Now let's understand how to define a nonlinear material. So I will just take you again to the PPT. So here you can see an elastic plastic material model shall be used for the analysis, and von Mises yield function shall be utilized. A true stress strain curve model that includes temperature dependent hardening behavior is provided in Annexure 3D of Section 8 Division 2. So we'll see how to do that in some other session. Time being, we are extracting the values of stress and strain at given temperature, or rather true stress and true strain at given temperature from the PTB3 manual, and we will directly put that into the our simulation software. Here you can see the material is 516 grade 70, the yield and the Poisson's ratio, uh, modulus of elasticity and Poisson's ratio is given, and then the plastic material model and this true stress strain curve is given. So let's get back to our software. So in the idealizations, we have assigned material SA516 grade 70. So I will just hit on the edit. When I have entered all the basic information about the modulus of elasticity, all tensiles limit and the yield limit, as well as the density and Poisson's ratio. Here is the tab called as nonlinear material. So once I hit on the nonlinear material, we want to have the plastic material, and there are the values of the strain versus stress. So just to make sure we start from the 0 0 for the stress and strain, we need to add one initial point 0 0, so that this the curve will start from the 0 0 point, and we can see the xy plot. So this is the true stress strain curve we can see for this material based on the values. So I will just cancel it. I have assigned the nonlinear material. So now we are ready to run the analysis. Okay, we have set the constraint, apply the loads. We have applied the nonlinear material, and I just need to right click and solve in NASTRAN. Just to save the time, I have already run the analysis and I will load the results. So we discuss about this material model and how to see the true stress strain curve. Now, okay, so this is the output from the PTB file. Uh, we can see the solid one mice stresses as well as the equivalent plastic strain from the model. S- We'll compare these results with our results, and will ensure that our results are matching very closely with whatever is done with the another software. So, and one more important aspect for the elastic plastic stress analysis. In elastic analysis, we need a experienced designer, because we need to classify the stresses based on their location and their nature. And then we need to compare those stresses with the allowable stresses. And if allowable stresses are more than the actual observed stress, then we can conclude that component is stable under given condition. But simplicity of elastic plastic analysis method, we need to do a nonlinear study which take a lot of time to run, and we need to use the nonlinear material model. But once the solution is converged, like we check for the three conversions: work, displacement, and load. If everything at every point converge 100%, then we can say the our component is stable under given working condition, and it is passing the criteria of elastic plastic stress analysis method. So post processing part is very easy if we go for the elastic plastic stress analysis method. Here we can see our solution has converged and we have the output. Uh, Really, the stresses in this analysis doesn't matter, because loads are already high and we are using the nonlinear material model. But our solution has converged. That itself is the proof that this vessel is stable and meeting the criteria of elastic plastic stress analysis method. So in stress, we can have these different kind of plots. Uh, uh, so here is comparison. This is from the PTB 3 manual, wherein we can see the nature or the distribution of stresses is exactly similar what we are getting in our analysis. And next one is the strain result. Here slightly different scale, I would say, so the values will not match, because they have taken the average percentage of equivalent plastic strain, and what we could get how NASTRAN is the solid effective strain. But if you see the plots like this one and this one, they are exactly matching to the one another. And the last but interesting part of any analysis is to matching the reaction forces. So how to do that? We know how much load we have applied in any particular direction, and we know the how much area on which that pressure or the direct load is applied. So we can sum that in one particular direction, and we check the reaction for the same from the NASTRAN output file in that particular direction. So here I have taken the y direction. So I know how much is the ID of the vessel, how much is the ID of the nozzle, and I know I have considered this quarter section. So I can take the projected area of this, and I know I have applied the 1008 psig pressure. So I multiply that pressure by the projected area, and I can get the force in y direction. So we are looking from the bottom to the vessel, and in another we have directly apply some thrust pressure on the race face area. So this we can sum up these things together, and we could get the total force in y direction. Same we compare with the whatever reaction force we are getting from the model, and we check the percentage error. So percentage error is less than 0.3%, and this implies our model is stable and our results are acceptable. So let's see how we can check the results in the uh, or the reaction forces in NASTRAN. So when I right click on the subcase one, there is reactions, and we need to select the area. So since we have considered the y direction, I will select the face at the bottom, and we get the reaction in y direction. So this is the same snap I have put into the my presentation. So the reaction forces are matching. So let's sum up what we intended to learn today. Can we use Autodesk Nastran to perform the design by analysis or the FEA to meet the ASME requirement? So answer is yes, we can. Can division 1 vessel design as per division 2 rules? So again answer is yes, and the answer lies in U2G and appendix 46 of section 8 division 1. We discuss about the mesh conversions. I demonstrated how to set up nonlinear material model, how to run the or the setup for the elastic plastic analysis in NASTRAN, and we verify the result, we verify the reaction forces into the this exercise.